having a quick demonstration of creating a Swift multi-platform app using PowerSync for the state management. So we'll start over here in Xcode by selecting a new multi-platform app. I'm going to call this demo app, and I'll create it in my local file system over here. Let me just recreate it. Okay, so as Xcode loads the Swift UI application and preview on the right, let me actually just make that like this. We'll see that we have a basic content view, which is being previewed over here. So for our application that we'll be making today, we'll be implementing a simple counter record, which will store a count integer, which will be incrementable in the app. We'll eventually have a view in this content view for doing all the CRUD operations on those counter records. We'll initially start out by implementing the counter record stores and CRUDs in a simple in-memory implementation. Then we'll incrementally adopt PowerSync for the download operations, for syncing uploads from a remote service, and then also uploads from the local client to the backend and other synced clients. So to start out, we'll first define our basic counter application in memory. And to do that, we'll define a struct to store that counter record. So let's create a counter record.swift file where we'll define our struct to hold that data. This will be identifiable and also equitable. For our record, we'll have a let ID of string. We'll also have a var for the count, which will be an int. We'll have a owner ID, which will be a string. And we'll also have a created at, which will be a date if we import foundation. This is the basic structure of our counter records data. In order to render this record in a Swift UI view, we'll also start out by creating a partial Swift view element, and we'll create that over here. Counter record view. We'll import Swift UI, and let's say our struct counter record view. Thanks to the autocomplete, we'll have a preview or counter record. This little view will render a single counter record, so we'll accept a counter as an input. And let's do that in the preview as well. We'll give it some demonstration values just for the demo. We'll typically use a UUID for this ID. Let me actually use an actual one for representing things better. And what's a UUID? And start with this little simple count like that. The owner ID, this will also be a UUID. And created at, we can fall back to now. So in order to render this, we'll have a very basic view of 2 rows and 2 columns. So in order to do that, let's create the first VStack. And for the first row, we'll have an HStack. The second row, another HStack. In this first row, let's start out with some text, which will display the count of our counter. And let's add a little spacer. We'll have some buttons over here soon, but in the second row, let's add some more text. This can be something like the created at, which will be counter.created at. Let's display that in an ISO format. And to the right, we'll have another text element. As such. To make this a little bit bigger. And in this side, we can add some buttons for mutating this counter record. So let's add a button. The label for this will be a simple image. We'll use a system icon. And for this, let's use plus in order to increment our counter. And you can have another button. And this image will be a trash can in order to delete this item. As you can see, the preview is over there. We want to manage the entire state of counters in an upstream view. So we'll also accept some callbacks for these buttons to perform the actions of. So let's do that over here. As such, and we can just run this here in the buttons callback. Okay, and we need to just apply that now over here. And everything should be well in our preview. We have our count, created that, owner ID, and some buttons over here to work with. Now we can go to our main view and start rendering and manipulating various counter records in that view. Start out over here, we can declare it will have some state, and that will be a variable state of counters, which is a counter record array, and we can default that to an initial array. In our app over here, we want to display a basic list to list our counters. So let's list them in the counters variable. And we can say counter in. For each one of these, we'd like to have a counter record view. The counter will be our counter. And we can fill this in soon. Okay, as you can see, the list would be displayed there if there are any records. We can then go ahead and add a button under the list in order to create a counter. So in our VStack, we can say a button. So we just simple text button saying add counter. And in this record or in this action, we'll append to our local state because we were currently first starting out by managing our counter records in memory. So say counters.append, and we can get a new counter record that we'll first quickly manage here. The ID will be a UID string count. We can start at 0 for this. And the owner ID, that will be our current user ID. Let's just create one here quickly. Search. And we created at, we'll say it was created now. And if we click this button, we should see that the state is updated and it's rendered over here. So in order to increment and delete these counters, we would like to manipulate this state variable cells. So let's start out by finding the index of this counter in that state. So let's say let the index equals counters dot first index. And since we're equitable, we should be able to say this. And let's do that. Let's just see. Sorry about that. Counters. And now that we have the index, we can manipulate that one. So we can say counters idx dot count plus equals 1. And for delete, we can say the same thing. We first get the index, and that is what we can do. So now we should have a little working CRUD view where we're managing counter records in memory state. We can create a few to be able to increment them, delete them as we would like. So in the next step, we'll be demonstrating how to perform these state management operations with PowerSync. The first step is to add our PowerSync Swift SDK via SBM to our Xcode project. We can do that by going to the build settings, general, and frameworks, libraries, and embedded content. Clicking the plus over here and saying add a package dependency. should allow us to copy our PowerSync Swift SDK's GitHub repository URL into this section over here. I've already added this previously, so you can see that once that is added, the option for PowerSync Swift should be available here. And we would like to use the version 1.5.1 less than the next major version. We can click Add Package over here, and this gives us an option of two different products. We'd like to use Xcode previews in this demonstration and in our development. So we'll go ahead and select the PowerSync Dynamic product over here, and we'll add it to our demo app target. After adding it, make sure to embed and sign PowerSync Dynamic, since we'll be using this inside the application's runtime. Okay, PowerSync library has now been added to our project, and we want to start using a PowerSync client for state management. In order to do that, we have to first define our client-side schema, which will be used for our local SQLite database. So we can go over here and create a new empty file, and we'll call it app schema. We can import from PowerSync, and we can say let app schema equals a schema. Our schema will consist of a few SQLite tables, so let's specify those now. Our first table name will be called counters, and it will have a few columns. The columns here are SQLite representable, as we'll see soon. So we'll have an integer column for the count, and we'll have a text column for the owner ID, and another text column for the created at value. Since this is normally represented as a date in our in-memory representations, we should just take note that for SQLite, this will be represented as a text string, but we'll be able to convert between those values when we query. This should be all the columns required for our counter record table. So now we can go ahead and actually integrate PowerSync with our current view. Switching back to the counters view, previously we were using a in-memory implementation for managing the state of counters. Now we'll slowly start to adopt PowerSync. So we can import the PowerSync library, and we can create a PowerSync client over here. Let's call it PowerSync. It will ask us for a schema, and we can provide the schema that we just defined earlier. We can also provide a database file name where the SQLite file will be stored in the file system. Let's call it app.sqlite. So now that we have the PowerSync client, we can use PowerSync APIs to access the SQLite database, which we'll be using for our state management. So the first step that we can start to look at is how does one create a new counter record using PowerSync. So we can go ahead and start porting over this buttons logic over here. So the first thing to note is that PowerSync's SQLite APIs are asynchronous and they can throw exceptions. In order to make this demo simple, we'll be handling that logic directly in this button. So the button context is synchronous, so the first thing we have to do is spawn an async task. In order to handle any exceptions, we'll wrap that in a do catch block. For the purposes of this demo and for easy debugging, we're just going to print any caught errors to the console. In this case, we could not create a counter, and we can display the error for debugging purposes if any errors do occur. So we can start out by instructing PowerSync that it's time to create a new counters record. We can try and await PowerSync execute. This will execute a new SQL statement. So let's give it some SQL. We'll use a multiple line string, and we can say insert into counters. Every table that is synced by PowerSync requires a unique ID column, which is automatically defined for us. We can insert the ID value, the count, the owner ID, and created at. And the values for that can be generated by a UUID function. The account can start at 0. The owner ID will be a placeholder value, which we'll receive from the application. And the created at value will be this string date format, which just represents the current time. The parameters for this query will be this one over here for the owner ID, which we can currently take from the user ID value over there. Let's just see, I might have spelled this wrong. Okay. So when you click the add counters button, let's just see if I can refresh this. The PowerSync client will now persist a new counter record into the database. Now let's think about porting over these onIncrement and onDelete functions. Again, the same logic applies where it's an asynchronous method which has to handle exceptions. So let's just start off by copying this. On increment, we don't have to do an insert statement, but we have to do an update statement. So let's update the counters. We'll set the count to equal the count plus 1, where the ID equals some placeholder value. And in this case, the ID of the counter we want to match is the counter.id value. And if there was an error, we could not update that counter. Let's go back to this, let's go back to the onDelete method now. And in this case, we'll delete from counters where the ID is that counter ID. Okay, that allows us to write changes to our SQLite database, but we still need a method of fetching that data from SQLite and PowerSync into the usable state, which we can map to our view components over here. PowerSync facilitates this by providing a concept called watched queries. These watched queries consist of a SQLite query in the form of a select query for fetching the relevant data, which is provided to the PowerSync database. The PowerSync database will then monitor the state behind the scenes and automatically report when there are any updates to that state. And that updated state will be provided to the consuming APIs. That way, we can monitor and react and present the latest state. So let's start by configuring that watch query for this view. We'll start that in a task over here, which will run while this view is present. The PowerSync Watched API can throw errors if there are exceptions, so let's catch those. And now let's start to construct our watch query. Let's start out by saying PowerSync.watch. And you'll see that there are some options over here for the watch options. Let's construct that. Provide the SQL that you would like to execute. This is a very simple query, so I'll do it in one line. And we'll order by created at. Okay, so PowerSync.watch over here executes a SQL query, and we need to instruct that logical function how to convert the SQLite result back into something which we can use in our application. And we can do this by providing a mapper, which takes a SQLite cursor, which can be used to access the various result set column values. So that gets specified as a trading closure. So we can say cursor in. We'll try and return a counter record, which needs an ID. And we'll have to fetch this ID from the results, which are presented by the cursor. So we can say cursor get string. The name of the column will be the ID. Let's do the same for the count. And use the cursor to get an integer. The name of the column will be count. And owner ID will be another string. And as mentioned earlier, the date can be mapped as well from the SQLite string value to a date value. So we start with an ISO date formatter, date from, and it'll be cursor, get string, name of that string being created at. Let's just format this a bit better for easy reading. And this value over here is actually technically optional, and we should never get to that case. So for simplicity, let's just fall back to the current date. So the PowerSync watch method can throw when returning an async stream of events. So let's try that. Now we have to actually use it. So for try await results in, and let's follow the for loop to here. So now this for loop will execute this code block whenever an update has been made to the counter state. That update will be represented in the result value as a list of counter records, which has already been mapped given this mapping function. So all we have to do is to take these results and bind them to our view application, which uses the counter state over here. And for that, we can simply say counters equals results. Doing that has now successfully wired up our PowerSync managed SQLite state for the counters records to our application. So now, as you can see in the preview, these are some counters that I've made earlier with a different database. I can delete them. I can create them more. And let's say 1, 2, 3. The fact that these counters are now stored in SQLite, which is a database on the file system, means that they are now persisted. And I can't really show that very easily on the previews, but if I start the application on my Mac, let's just give it a few seconds. You'll see that I have the same SQLite database, which is being used in the previews in my actual application. Freshly starting the app, the state was available, but I can create a fourth one as well. I can stop it. And if I restart the app, that state should be there again because it has been persisted. Okay, so now we have PowerSync managing the state of our counters in our view. We can mutate the state locally, but the real power in PowerSync comes from its syncing abilities. So in the next step, I will show you how to connect this local PowerSync client to a PowerSync backend service, which can download updates from a remote database. In order to sync a local PowerSync client, we require a PowerSync backend service. That PowerSync service will connect to a database that you provide, and it will replicate the data which you would like to sync to clients internally. The clients will then connect to the PowerSync database in order to download updates which should be applied to the local state. So we'll quickly switch over to our browser over here, where we'll see the PowerSync dashboard, where I have configured a PowerSync instance for testing. In the instance configuration, I have defined a set of sync rules. These sync rules are currently defined to sync all the counter records to all devices. This is a very simple global bucket. More complicated sync rules are possible, but for this demo, we will be syncing all counters to all devices. This PowerSync instance is configured to connect to a source database which is hosted by Supabase. That database has a simple counters table present in the Postgres database. We also require a method of authenticating clients to this PowerSync service. The PowerSync service requires a JWT when clients connect to it, and that token needs to be authenticated with a backend service which you provide. For our demonstration purposes, we'll be using Supabase for the database, the backend CRUD API, and authentication API. It's an all-in-one solution from the Supabase side. So in our Supabase dashboard, we also have a project which the PowerSync service is linked to. And this is the counters table, which has a few random counters which I've created previously. We would like to integrate our PowerSync client to these services. So let's go back into Xcode. So what we need to do is we need to, first of all, connect and authenticate to the PowerSync backend service from a client's perspective. The client needs a method of connecting to those services. And in order to do that, we need to implement a backend connector. So let's go over here and we'll call it Supabase connector.swift. Let's import from PowerSync. And we will have a class over here of the Supabase connector. That's not necessarily correct. So PowerSync backend connector protocol. If we try to save that, we'll see that we didn't implement the methods. Let's quickly have Swift implement that for us. So in order to download, we need to be able to provide credentials that this client can use to connect to the PowerSync backend service. Uploads are also handled by this connector, but we will handle that in the next step. So let's mark that as to do for now. We need to be able to return PowerSync credentials. This requires an endpoint to the PowerSync service, and it also requires a token to use to connect to the PowerSync service. That token will be verified with an authentication service. In this case, we'll use Supabase for that verification and user management. Excuse me. So we need to actually interface with Supabase. In order to do that, in our project, we'll have to add the Supabase SDK. You can go over here to Frameworks, Libraries, and Embedded Content, and we can add a package. You would have to select the Supabase Swift SDK's GitHub URL and paste that here. I've done this already, so you'll see that I have Supabase Swift listed as an option over here. I'll add that to the project quickly. I would like to add Supabase to my app. It's authentication and Supabase over here. Now we can go back into our backend connector. We need to instantiate a Supabase client. I'll import Supabase. In order to do this, you need to create a client, which requires a URL to your Supabase API and a key. I've copied this conveniently earlier. Let's also import foundation for the URL client. Now that we have the Supabase client, we need a method of obtaining a session. So let's create a method over here. And I believe this should be a session. We can say client.auth.session. This throws, so let's try it first and say if we don't have a session, we can try and sign in. This is an async function, and it probably throw as well. Okay, let's see, you may say await over here. So if we have a session, this won't throw and we'll get session returned over here. If we don't have a session, this will be null and we'll reach this guard block. In that case, we can say client.auth.sign in anonymously. And this might also be a try wait. And we can return the session provided by that. So in the method over here, which the PowerSync SDK will call when it requires credentials, we can now use those credentials. So we can say let session equals try await get session. For the token, we should be able to get that here. It's the access token. So this is the PowerSync endpoint, which we can get from the PowerSync dashboard. So get that over here, copy that over. Okay, so now we have all the credentials required to connect to this PowerSync service. This service will replicate our Supabase database, given the sync rules that we've specified, and send the required data to clients that have connected to it. Let's go into our code over here to actually instruct PowerSync to connect with that client. So in this task over here, we can actually create a button to instruct that to happen. So let's see over here. We have our add counter button. Let's add this inside of an H stack. So we can have a few buttons next to each other. And in this context, let's see over here. Let's add a spacer. And we can add a new button, which has a label, which is text saying connect. And in this, it's again another task, which can throw. And let's actually run this, try away, PowerSync, connect. You don't need to supply these options at this point. Let's create an instance of our Supabase connector over here. And when we connect, we should instruct PowerSync that that is the connector it should use for credentials. Such. So when we push the connect button, that should fetch the state from the remote PowerSync service and apply it. For some ease of access and management, let's also add some more buttons for various other operations. Let's add a button which disconnects from the PowerSync service and clears the local SQLite database. And I'll explain why we'll add that functionality soon. So disconnect and clear does not require any parameters. Okay. So as the PowerSync service is connecting and disconnecting to the remote service, we might want to be able to display a nice status of, is it offline? Is it online? Can we display that to the application? And we'll do that with a simple status icon. So let's first define a place to store that state of the icon. Let's say add state, it's a variable, status image name, and we'll call this Wi-Fi /. Initially, we won't be connected, so we'll display that we are not connected with a Wi-Fi /. We need to fetch the current status information from the PowerSync client. We need to watch that as well, so we can do that in another task. Just in case there are any errors. I believe this one might also throw. So we can say for status in PowerSync, the current status.sflow. Let's see, try. I think I might have made a mistake over there, but let's just say over here. So I think I might be incorrect. Let's see, it's this. Okay, there we go. And let's see over here. What we want to do is we want to set the status over here based off what the current status is. So we can say if status.connected, we'll say status image name equals Wi-Fi, things are all good. Else if status.connecting, let's call this exclamation mark. Else we aren't connected, Wi-Fi dot slash. Okay, let's see. This might be unreachable. I might have been incorrect about that API. Let's see. No, that is not unreachable. I'm just going to ignore that for now, just to make them move on. Okay, so now we have a status watch over there, and we should have an update over there. Now we need to actually display the status over here. Let's display that in the H stack over here. An image where the system name is the status image name. Okay. If I have done that correctly, we should have everything we need. Okay, we should be able to resume this over here. So the way PowerSync syncs data is that you can have local mutations and you can also have downloaded mutations. The PowerSync client will first prioritize uploading the pending uploads to the service before applying any new state coming from the PowerSync backend service. Now, in our case, we have only implemented local mutations and downloads. And the local mutations which we have implemented should result in uploads. And we haven't implemented a mechanism for uploading those changes yet. Due to that, the PowerSync service won't apply the upstream state directly. So in order to work around that, I'm going to discard the local changes that I have just made and allow the local client to sync on the remote PowerSync service. I'll make some changes on the remote and we should see that they should be streamed to the client. Once we implement the upload flow, we should have bidirectional sync. So the Supabase app is asking for my keychain. Let me just quickly allow that. Let's try it again. Okay. So we have our app here. These are the local items that I've created previously. If I connect, I should see a connecting status. That's a good point that I almost forgot about. This is a Mac app and it's sandboxed. I need to allow network access. So let me go over here to signing and capabilities, and I will allow outgoing connections. Let's go back to our content view and see if we can connect. Yes, we were able to connect. That's a solid Wi-Fi symbol. But you'll see that these are still my local state items compared to what is currently present in Supabase. Let's go over here and disconnect and clear just to delete that. And if we connect, we now see that we've immediately synced the data from the Supabase database. I can update this value in Supabase to 9001. And if I switch views, you should see that we now have that reflecting over here. Let's do some more random edits just for fun. We now have one that has one value, and we are now downloading synced updates from our remote database to our client. The next bit of fun will come in once we implement uploads and sync bidirectionally. That will be in the next section. In order to implement uploads, we have to implement the connectors upload data method. Now, the upload data method is called automatically by the PowerSync SDK once local mutations are pending for upload. The connector needs to make API calls to the backend, which is connected to the database replicated by the PowerSync service. This implementation is up to the developer to implement. We'll be using the Supabase APIs to perform those updates. The implementation here is generally quite a bit of typing, so I will be cheating by copying and pasting. But for context, the PowerSync database provides methods for getting the items in the CRUD upload queue. One could say guard let transaction equals try await database.get next CRUD transaction else return. So if there is no transaction, this will just return early. But if there is a transaction, this transaction has an array or a list of CRUD items. These CRUD items are operations such as put, patch, or delete operations, which were collected as local mutations were made on the application. The upload data connector can make relevant API calls for those put, patch, or delete operations to the backend. I'm going to quickly just paste in that implementation for Supabase over here. So you'll see that we typically go with an upload data function. We get the next transaction, and we keep track of the last CRUD entry. We keep track of this in case there are any rejections or failures on the upload data path. Those kinds of rejections could occur from invalid data, which might have been created locally, which needs to be rolled back on the local state, or if there are any other errors in the upload path, which require rolling back of certain transactions. So the general procedure is to loop through the CRUD items of a transaction. In this case, we'll get the relevant table that that operation occurred on, and we will instruct the Supabase client that we want to make a mutation on that table. Depending on the type of operation, we will select the relevant Supabase API given the data of the operation. That API will then write the changes to the Supabase Postgres database, which will be processed by the PowerSync backend service, which replicates that database. And any relevant state changes will be synced back to the client, resulting in a fully consistent synced system. Once we've finished uploading all of the CRUD items, we typically mark this transaction as completed. Okay, if there are any errors in uploading that, we differentiate between two different kinds of errors. Those are errors which are recoverable and those which are not. Typical recoverable errors are network errors, which will simply retry the upload at a later stage after a short delay. Unrecoverable errors are things like row-level security issues, which there might not be sufficient privileges for, constraint violations, or data exceptions. In that case, we don't actually write anything to the source database since this fails, but we still mark the transaction as complete. After marking the transaction as complete, these items are removed from the CRUD queue, and the local PowerSync client will apply whatever state is resolved from the upstream PowerSync database. Since these changes are not in the upstream PowerSync database state, those changes will be reverted. Okay, so this is the basic flow for taking the list of CRUD operations and applying them to a backend. We also have a set of error codes here just to facilitate helping to determine which types of errors are fatal and which are recoverable. Okay, so we have our upload data method over there. Let's do a few more miscellaneous tasks to make the upload flow make a bit more sense and be more complete. So now we are signing in with Supabase, and in our application, we previously created a random UUID over here for the user ID, which created counters were associated with. Since we now actually are signing in with Supabase, we can use the session provided by Supabase as the user's identification instead. So let's delete that. And let's replace the insert operation with that value. In order to do that, I'll need to import Supabase to use its typings. And we can go over here and use our Supabase connector, call the client or current session, which is an optional value, the user.id as a UUID string value. One thing to note is that this value is technically optional because there exists an case where the app could be started while offline, where we are unable to connect to the Supabase API in order to get a session. That will cause the current session to be null, which is a case that we can account for in our application. But let's start accommodating that in our typings first. So the counter record now might have an optional owner ID. The counter record view can display a little placeholder over here when that is the case. And in our watched query, we must remember that owner ID is now an optional value. If this value is not present and we chose the getString mapper, that would throw an exception. In order to simulate that case later, let's actually add a button over here which performs that sign out operation. So we'll call our Supabase sign out. If there's an error, we could not sign out. Label that sign out, and let's fix this typo over here. Okay, we should be able to preview this now. And we see that we have a single counter currently present in my database, which was created without being signed in. Since I started this app offline and I started this from a clear state behind the scenes. Now, what will happen is that this item has been created in the background. While there was no session, the owner ID is set to null. PowerSync will queue this creation as a CRUD operation, which will eventually make its way to the upload data method. Since this was a newly created item, this will be a put operation, and we'll get the various data from the PowerSync CRUD operation. The value will be null, but we can luckily use the current session, which is provided when we actually are performing the uploads. We can default that value, which we will send to the Supabase API. And that will write the full record to the database, which will be processed by PowerSync and eventually be synced back down to the client, updating the local state as if the owner ID has been set. So let's go over here. We are not connected yet. I go into my Supabase database. Let me just refresh this. These are the current cloud counter records. So if I go over here and if I maybe set this value to a unique 5, we can connect it. And we'll see that we have the downloaded records that were in the cloud database, our previously local created one, and the owner ID has now been updated. If I go over here, I should see that as well. If I wanted to, I could update this value in the database, which would simulate another client being connected to the application. And that should be synced down to the device over here. Perfect. So what we've done so far is demonstrated a single client and some remote updates. It is also possible to simulate and run multiple devices on our same dev environment, just to give a quick demonstration of what it looks like for 2 instances of the application. I'll do that now. Okay, let's start the Mac version. That's running over here. And in order to run this a bit nicer on iOS and to be able to click the buttons a bit easier, I'm just going to do some button styling on these ones. Okay, let's run that in an iPhone. And let's get the two devices side by side. Also on connect my Mac app to the PowerSync service. And now I will create a local counter here and then connect that one as well. And we should see the same list of items between the two. It's about to increment this one and it should reflect immediately on the other side. I can then also perform a change over here, which should reflect on this side. And delete this item, it's deleted, and delete this one, and it's deleted. And then we have demonstrated syncing between multiple different devices with PowerSync. Thanks, guys. That's everything from my side for this demo. Thanks for your time.